Okay. All right. We go ahead and record. So we started on
We
the
have the, sorry, Zach, we have the skinny white rectangle.
skinny white rectangle. Okay. All right. Weird. Okay. How about now? All right. Thank you. All right. Okay. So last time we introduced the method of stationary phase. And the idea here is that you have some Fourier type integral with a rapidly oscillating function with some amplitude modulation. Okay. And so x psi t, okay, is the phase, and then f of t is the amplitude. And the idea is that the rapid oscillations lead to cancellation of adjacent parts of integrand, mostly, except at the endpoints. Okay. So you have some function, and if this is 0 or something here, right, these are canceling each other out. Okay. This is your amplitude f of t, okay, and then x psi of t is going to determine the shape of the oscillations. But given that x is large enough, these are going to be rapid enough that each lobe of the oscillation is going to have a pair that's going to cancel it out, except at the endpoints, because they may not stop and start in phase. So to leading order, you can essentially approximate using the endpoints. The method of stationary phase, okay, finds the stationary phase point in your function psi of t. Where essentially psi prime of c is equal to 0 and expands around. Okay, so this idea, okay, will lead to an integral that you can take using integration by parts, and you're just going to get the endpoints. Okay, if you have this situation, however, okay, it's not going to be as simple as this cancellation story. You're going to have to find the stationary phase points, and those are going to be the primary contributors. The lemma that sort of allows you to do this is Watson's lemma. That's going to apply in the regions where phi prime is non-zero, let's say where phi prime is positive everywhere. But if you have points where phi prime of c is equal to 0, that's going to be sort of the frozen points of your exponential, and therefore the primary contributors to your integral in this case. And the integral that comes up often in this case is going to be the integral over e to the I z squared dc. Okay, so and stationary phase finds stationary points and then expands around them. Okay, to give a Laplace-like approximation. Okay, so in that case, you end up with something like that is for I of x equal this integral, right? Then if phi prime prime of c is not equal to 0, then psi of t is equal to psi of c plus psi prime prime of c over 2 t minus c squared, and then you just retain that quadratic approximation. Okay, so in this case, I of x is going to be approximated by f of c e to the I x psi of c plus I mu pi over 4 square root of 2 pi over x psi prime prime of c, okay, where mu is equal to the sine of phi prime prime of c. Okay, so you see here, right, this idea of Taylor expanding the amplitude around the point C and Taylor expanding your phase function psi around C. And then you have to perform some contour integration, or there are other ways to get this integral involving the I times t squared terms here. Okay. So, so this is the idea. This general principle, right? It holds in between the stationary phase points, okay? But if you have stationary phase points, you can't just essentially assume that the endpoints are going to give you your primary contribution. If you have a stationary phase, the primary contribution is going to come around the stationary phase points. And that's where the method of stationary phase comes in. Okay. So I'm going to just do a couple examples for now in actually solutions to PDEs that involve this method. Are there any questions about the general approach before we move on? Okay. All right. So let's get to applications. Okay. Now let's remember back to PDEs. So long time scale asymptotics for linear dispersive waves. Okay. So let's say that we have some linear constant coefficient PDE, and in particular, an initial value problem on R, okay? So U sub t of xt is equal to the sum from j equals 0 up to n of aj dj dxj u of xt. X lives on the reals, t is greater than 0, and then we're going to have an initial condition, u of x0 equals u0x, defined on the reals. Okay. So, and let's say that u of x goes to 0, x goes to, as x goes to positive infinity, okay, sufficiently fast for a bounded solution, an integrable solution, okay? So as long as we have this sufficient condition, what's one way of solving this PDE that we might use?
Method of characteristics.
It might be hard. So once we go to higher order derivatives, right? Yeah, method of characteristics will sort of work well for
Oh, I'm sorry.
first order derivatives, right? But higher order might be, you can do it, but there's probably a simpler way.
Would use a Fourier transform.
Yeah, so that's one way to do it, or you can sort of guess wave functions, which is similar to just using a Fourier transform kind of ansatz. Okay, so one way to solve is using Fourier transforms. Okay, and maybe now you can start to predict where our method of stationary phase problem is going to come in. It's when we try and invert back from our Fourier transform. Okay, so what's a Fourier transform? Well, it's a function f hat of k that you get by taking the integral of some function against e to the minus I kx dx. And then you can invert that Fourier transform. This is just one convention. It's the one we'll use by taking 1 over 2 pi integral over the reals of f hat e to the I kx dk. Okay, so the typical way that you solve using Fourier transforms, move everything into Fourier transform space. Derivatives just become, products with your Fourier variable. You can solve it as a linear ordinary differential equation, invert back, okay? So the idea then is that u hat sub t is going to be equal to the sum from j equals 0 up to n of aj minus ik to the j u hat, okay? And this is just a time derivative equals some polynomial multiplied by u hat in this case. So we can work this out, and we get that u hat of kt is equal to u0 hat of k, just the Fourier transform of our initial condition here, okay, times e to the I kx. Sorry. Okay. E to the minus I omega of k t, okay, where omega k is equal to I from j equals 0 up to n aj I k j. Okay. All right. So this is the dispersion relation, okay? And then in general, our solution to the PDE, u of xt is equal to u sub 0 of k e to the I kx minus omega k of t dk, right? So, so what we have now, right, is a Fourier type integral, okay? This is assumed to be something that we know, right? But if you look now, our psi of t function is going to be one that we can get by factoring out an x here, right? And so it's a little bit different of a form than we've seen before, but we'll talk about how to manipulate our way there, okay? And the idea is that we're going to focus on omega of k's that are real and such that omega prime prime of k is not just equivalently 0 everywhere, okay? So that'll give us an omega of k that's going to lead to the psi of k that we can that we can asymptotically approximate using that Taylor series. Just to make this more concrete, let's look at the following dispersive wave equation. Okay, and on your homework, there's kind of a variation on this, and you'll just dig a little bit more deeply into this problem. Okay, so this is like a linearization of the KdV equation that we studied some in PDE. Okay, so here's your initial value problem again, right? We could again just use Fourier transforms, but just to be a little bit more explicit, you can also sub in just the wave function, right? So just assume that you know an ansatz, which would be the form of your solution. If I plug this in, then I get the relation minus I omega plus aik minus I k cubed e to the I kx minus omega t is equal to 0. I can solve this for omega k is equal to a k minus k cubed, right? If the k cubed wasn't there, right, we would just have our typical transport equation, okay? But because the k cubed is there, then you're going to have dispersive waves. You're going to have waves that travel at different speeds depending on their wave number. Okay, so as you visualize waves propagating in space, right, the higher frequency ones are going to tend to move slower up to some point. Okay, and the broader ones, okay, that have a lower wave number are going to tend to move faster. And our general formula for u of xt now is going to be the inverse Fourier transform of u0 hat e to the I k x minus a k minus k cubed times t. Okay. So if you're thinking of sort of analogy with Fourier series, right, these are our sort of individual components, right? And this is going to be like our infinite summation over all of these wave numbers in this case. We're integrating over all values of k, right? So we want to figure out what's happening with this solution, right? And maybe for some forms of u0 hat, we could perform this integral. But in general, maybe we're only interested in, let's say, the long time scale dynamics, okay? So if I don't know much about my initial condition, okay, but I have some data where I know how the wave structure has settled over a long time, okay? What are my long time scale asymptotics going to be, okay? So in this case, we're sort of flipping things around because we have our value of t, right, is the thing that's going to be large in this equation. So let's sort of formulate this in terms of a method of stationary phase problem. So in this case, we have that if I rewrite this, e to the I kx minus omega t dk, right? And I'm going to write this as 1 over 2 pi integral over the real u0 at k e to the I t now, okay? And I'm going to have a function which I'll call psi, which is going to depend on k. Now it also depends on t and x, right? But the k is going to be what I'm going to differentiate in, okay? So if I look at psi of k, what is psi of k going to be? It's going to be k x over t minus omega of k, right? So this thing is a Fourier integral, okay, with a stationary phase, which is going to be given by the critical points of this phase function, okay? What is that stationary point? In particular, it's going to be psi prime of k0 is equal to x over t minus omega prime k0, where that equals 0. So I get that that occurs where omega prime of 0 is equal to x over t, okay? So in other words, where k0 is equal to w prime's inverse evaluated at x over t, okay? So this is what we'll call k0 of x over t, right? So if only a single such k0 exists, okay, then we can use stationary phase formula, right, which we wrote down earlier, in order to derive our stationary phase. So we proceed as before, right? We are going to Taylor expand this function about the stationary phase point. We would also Taylor expand the amplitude, but we're just going to evaluate it at k0. And we're going to be left with our leading order approximation to this Fourier integral, which is going to be u hat 0 evaluated at k0 x over t divided by the square root of 2 pi t psi prime prime of k0 x over t, okay, and e to the I psi of k0 x over t plus I mu pi over 4. Okay. And in this case, mu equals, again, the sine of phi prime prime k 0. And this is true as t goes to positive infinity and as x t is equal to big O of 1. Okay. So this is, true over a broad range, but you just can't take x all the way out to positive infinity faster than t. Okay. All right. So I'm giving you the general sketch here. You'll have a chance to explore this more in a homework problem of a slightly simpler case than this one. Okay. Questions about this approach? All right. So hopefully you're starting to see that, these integrals are going to come up in solutions to other problems, right? Fourier integrals especially come up when you're using inverse Fourier transforms. So let's consider another example, okay? This is another initial value problem from quantum mechanics called the free particle Schrodinger equation. Okay. Again, it's a type of wave equation, and it's assumed that this amplitude we call psi of x. Its initial condition is going to decay to 0 as x goes to positive infinity. Okay, we're going to assume it's properly integrable. Okay, and the interpretation in quantum mechanics is that psi of xt squared is going to be the probability of finding the particle in a small region around x. Okay, so the solution to this is really going to give us some probability density function associated with a particle moving according to some physical laws. All right. Now it's kind of a linear type wave equation. Again, it sort of looks like a diffusion equation. We can take our approach from the last problem and say, well, let's substitute in an ansatz, right? It's a linear problem. And I'm going to assume that I have some wave type solution. If we do that, then we end up with I minus I omega plus I k squared, e to the I kx minus omega t is equal to 0. Solving this, we get omega of k equals k squared. And so that means that I can write the solution, psi of xt, as 1 over 2 pi, the integral from minus infinity to infinity, the Fourier transform of my initial condition, e to the I kx minus k squared t dk. All right. So again, we have another Fourier type integral. Okay. We can find the stationary phase point of this argument up here. Omega prime of k0 is going to be equal to 2k0 is equal to x over t. This implies that k0 is equal to x over 2t. And we get that omega 0 k0 is equal to 2, which is greater than 0. Okay, so we have a non-trivial second derivative at our stationary phase point. If we again apply the method of stationary phase, remember, to leading order, we just use our amplitude evaluated at the stationary phase point, divided by 4 square root of 4 pi t. This is now involving this second derivative at k0. And we have e to the I x over 2t squared times t. So that's our value k0 squared times t minus I pi over 4, okay, plus some terms that are going to be little o of 1 over square root of t. Okay. So the leading order now, we have our form of a function that approximates our solution here. Okay, just looking back at our original Fourier integral approximation here using stationary phase, right? We have our leading order term, right? We have our square root of 2 pi over our whatever our function is that's large. In this case, it was t. And then we have our phase formula psi prime evaluated at t. Okay. So in this case, it was, it wasn't called psi, but it was this function here, right, that lived in our the argument of our exponential. The additional 2 pi comes from the fact that we have this leading factor of 1 over 2 pi. So that's why you find a pi now in the denominator of this function here. Okay. So this is our approach, right? So you can see it'll probably work on most linear PDEs that you can solve using Fourier transforms. So it's a very powerful technique in that regard, because even for nonlinear PDEs, right, you can often linearize and approximate in that way, or perform some sort of stability analysis using a linearization of a nonlinear PDE, for instance. And so method of stationary phase comes up a lot in that sense in the solution to the PDEs on unbounded domain PDEs. Okay. All right. So any questions about stationary phase? Okay. So yeah, you'll have a PDE example and then another example on homework to work through. The last method that we'll talk about in approximating integrals before we move on to differential equations is what's called the method of steepest descent. And I want to try and build up some intuition for the method of steepest descent. Sometimes it's called the saddle point method if you only use the leading order. And so that should conjure up some visions of the fact that you have some function and you're somehow looking for the saddle point rather than necessarily a maximum of it. Okay. The reason you think of a saddle point is that often these are posed on the complex plane. Okay. And so you're going to draw contours and you're going to find some contour that has a point on it that has a saddle point. So it's, it's a max if you look in one direction, and it's a min if you look in another direction, okay? So the idea with method of steepest descent is that you want to seek asymptotics of the following type of integral. I of x is equal to some contour integral, f of t e to the x rho of t dt for some large x, okay? And rho of t could be complex valued, okay? And c is going to be some curve in the complex plane, okay? And also, you know, f of t could also be complex value, okay? So even if you have real integrals, you can always sort of pose them in this way, right? If you just have a contour along the real line, you can sort of realize it as some sort of, you know, contour integral. And there's really two competing effects that you want to consider in these integrals, right? Especially because x is large. And one of these is the exponential growth and decay due to the real part of rho of t, right? So if this is just some real function here, it's multiplied by some large number. And so if it's negative, it's going to rapidly decay. If it's positive, it's gonna rise very rapidly. Okay. But now think back to the method of stationary phase. If this function is complex, it can have an imaginary component as well. And now you're not talking about exponential growth or decay, but rapid oscillations. Okay. So the other component is oscillatory cancellation. Okay, due to the imaginary part of rho of t, right? So now these two ideas from Laplace's method and method of stationary phase sort of come together in one integral, okay? So this is a generalization of Laplace and stationary phase methods, okay, which is why we are covering this last, okay? Moreover, we're going to have to use some methods from complex analysis, okay? Just complex integration. So there's a few ideas here which I'll sort of fly by, okay? The first of these is the idea of what are called Koshi-Riemann equations. What are these? It's sort of a way to get you to harmonic functions in the complex plane. So if I have some analytic function f, it's a function of some complex number, okay? I can write it as u of xy plus I v of xy. And if x, y, u, v, okay, they're all defined to be real valued. And as I said, I want f of z to be analytic in z. Then this implies the following things, that u sub x, partial derivative of u with respect to x, is equal to partial derivative of v with respect to y. V sub x is equal to minus u sub y. And taking these things together, I can write uxx plus uyy is equal to 0. Vxx plus vyy is equal to 0. So u and v are harmonic, okay? Now, what we know about harmonic functions is that we are not going to obtain, well, yeah, sorry, we'll circle that back to that later, okay? But the idea is that if we have some analytic function here, we can always break it out into the sum of the real and imaginary parts, and those components are going to be harmonic, okay? That's the idea behind the Cauchy-Riemann equation. All right. Second idea is Cauchy's theorem. What is that? We've used it before to compute one of the integrals last week. And that the idea there is that if f of z is analytic, okay, in a simply connected domain, then along a simple closed curve C in D, the following thing is true, that f of z dz is equal to 0. Okay? We're going to use that a lot in order to compute these contour integrals. The last fact from complex analysis is that if we have the same setup as above, okay, but f of z has a number of isolated singular points, okay? We're going to add that condition to F now, and we'll call these singular points Z1, Z2 up to Zn, okay? Inside C, then the following thing is true, the integral of f of z around C is going to be equal to 2 pi I, the sum from j equals 1 up to n, aj, okay? Where aj is what's called the residue of f of z, zj, okay? So just to remind us of residues, right? So for example, for a simple pole, typically the residue is just going to be the factor that appears in the fraction with that singularity in the denominator, right? So another way of writing this is the limit as z goes to c of z minus c f of z, okay? So the so for f of z is equal to 1 over z minus 1, the residue of f at 1 is going to equal 1. That's what lives in the numerator there. The residue of this function, f equals 2 over z minus 1 minus I, at that singularity is going to be 2. Okay. All right. So yeah, so in general, right, you can just read these off for these simpler poles. There's other formulas in the case of more complex residues. Okay. Like, yeah, if you don't just have a simple pole. All right, so that's Koshi residue theorem. Okay, that's our three complex analysis facts that we're going to use in order to help us move forward. Okay. Has everybody had some semblance of complex analysis? Is anybody? Okay, I'm seeing some thumbs up. Okay. All right. I don't want to belabor these points too much if it's old hat for everybody. Okay. If you need some extra background materials, just on complex integration, let me know. I can find some lecture notes or a handout and put it in Canvas. Okay. We got about 4 or 5 minutes left. Let me just maybe get started on an example, and then we'll stop. Okay, once I set it up. Okay, so how can we use method of steepest descent? So let's consider the following integral. Cosine of kx divided by x plus b squared plus a squared dx. K is some frequency greater than 0, a is greater than 0, b is some real number. Okay. And let's start by rewriting this as a Fourier integral. You might say that, well, then why don't we just use method of stationary phase? Okay, so we'll see in a little bit. Okay, so I'm going to have something I'll call the real part of I plus, right, of x. This is equal to the real part of the integral from minus infinity to infinity, e to the I kx divided by x plus b squared plus a squared and dx close parentheses there. Okay. All right. So what I'm going to do is introduce, in order to compute this, a simple closed contour C. Okay. So the idea is that something lives down here. We suspect that we're going to have some poles that we may have to deal with using residue. If I draw this, the complex plane for this problem out, so real part of, well, I guess I'll stick to the variables that I have. Real part of x and imaginary part of x. Okay. I'm going to draw the following contour. So this is a contour that we're living on in the actual integral. Okay. Let's take it large, but not infinite, so that we can draw this kind of half circle. Here's some r greater than 0, and here's some curve, which we'll call CR, that wraps back around. Okay. Here's a pole for that function that lives inside, IA minus b, right? So if we find the roots of this polynomial here, this is going to be one of them, okay? And that's the only one that's going to live inside of here. So for large R, the only singularity of the integrand inside our contour C is this point we'll call Z0 equals IA minus B, okay? And that's going to be a point of interest there. So then let's use residue theorem there. The integral of f of z dz is going to equal 2 pi I residue of f of z evaluated at z0. And in particular here, our f of z is, well, it's just our whole integrand up there. I kz divided by z plus b squared plus a squared. Okay. All right, so the residue of f z0 is equal to the coefficient of 1 over z minus z0 in the expansion near z0, right? Because it's we computed from this limit. So f of z I can write as e to the I kz over z minus ia plus b times z plus ia plus b. So that's the singularity that lives outside of there. The leading order, we can approximate this as e to the I kz0 divided by z minus z0, z minus z0 conjugate. I guess that was an equality, but this, the leading order then is e to the I k z0 over 2ia. Okay, if we just split it up by partial fractions, 1 over z minus z0. Okay, so now this is our amplitude or numerator, if we wish, of that, right? And so the first part in this process is to get this contour integral, and we can, right? So we get 2 pi I, the residue of f z0, so that's equal to pi over a, e to the minus ka, e to the minus I, dk. All right. Now, the next step in this process will be to check what the other parts of the contour integral are, and prove that that this part vanishes. Okay. But I'm gonna have to stop for today because we're a little bit over time. But the idea of this integral is that we want to motivate the use of these kind of closed contour integrals in order to address the fact that the main contributions to these integrals tend to be these singularities. They're sort of like serve the same purpose of our stationary points and method of stationary phase. But the ideas get a little bit more complicated. Okay, so I'm going to have to stop midstream on this example, but we'll circle back to it at the beginning of Friday. Okay. Any questions on this? Sorry to go a bit over.
This is just a bit more conceptual, but for Laplace's, it kind of made sense to expand around maxes because that's like the largest contribution. Should we think of stationary phase as like at these points, it's not canceling out like the two lobes because the phase isn't changing as rapidly?
Yeah, so there your rapid oscillation starts. So everything to the side of that in stationary phase is rapidly oscillating, so you're getting cancellations. But right at the stationary phase point, it's sort of like, an interior end point or something like that.
Okay, so that's why it's fine to have a min as well. We're not looking just for the maxes of those places. That makes sense.
Yeah.
Gotcha.
Is the integral of the real part of the integral? Do we use that up at the top?
Yeah, you can. Right. Yeah, you can pass that in.
Okay.
In that case. Yeah, because I'm just using the like Euler's formula for complex exponentials. All right.
Thanks, Zach.
Yeah, thanks everybody. So see you on Friday or see you in office hours otherwise. All right. Have a good day.
Bye.